So with these two particles, both being positively charged, we may write down the resulting force that they interact with. So the Coulomb force for this particular scenario is given as the charge, the product of the two charges involved, divided on this 4 pi epsilon 0 r squared. So it looks like this. Therefore, the resulting Coulomb potential looks like this. So keep in mind the relation between these two quantities, that F is the negative gradient of the potential. Now, we have encountered this type of potential before. This is in fact a Kepler problem. With one twist. Namely that this constant k is now negative. This has profound implications for the type of orbit that we can expect. Because the positive sign implies that the potential energy will always be positive. So we have a repulsive force. And so the total energy also has to be positive. And this is in contrast to the Kepler potential, where we could have a negative energy and therefore a bound orbit. But in this case, there is no reason to expect any bound orbit because the energy is positive. And if the energy is positive, we can in fact immediately infer what kind of orbit we should expect. We see that positive energy means that the eccentricity has to be larger than 1. And if you then consult the table that we set up in the previous lecture, you will see that this corresponds to the case of a hyperbole. All right, so let's then try to analyze this using our equation which describes the trajectory. So we had r is equal to p over 1 plus epsilon cosine beta. So we used theta before, but since we have reserved that for the scattering angle, we're now using beta. But there's one thing we should revise slightly here to make this general. If you recall the Kepler problem, we made a choice when integrating the equation of motion to obtain this. Namely, we set the integrational constant theta 0 to 0. And we then showed that theta 0 being equal to 0 corresponds to the polar angle being measured from the period. So that if this argument is 0, then R would be minimum. It would be a local minimum. But in general, the general solution without making any assumption about the initial conditions would look like this. Right? So we have this is what we know. Now, the reason for why I've inserted or reinstated this beta 0 is a sign consideration here. Because we have that the orbit parameter p is defined as the angular momentum squared over the mass and the strength of the potential. In the Kepler case, k was positive, so p would be a positive quantity. In our case, or in the present case, k is negative. So p is smaller than 0. And this means that we can rewrite this equation as like this. The reason for why I've done this is to show you that we now have to choose beta 0 to have a different value if we still want beta, the angle, to be measured from the period. Beta 0 equals 0 no longer corresponds to the period. Instead, in the present case, this is obtained when beta 0 equals pi. So if beta 0 is chosen as pi, I get cosine beta minus pi, which is equal to minus epsilon cosine beta. And the equation can be written like this. So this left-hand side is now a positive quantity, exclusively. It's always positive. And since epsilon is larger than 1, you see that beta equals 0 will correspond to R being minimum. And moreover, from this equation, it follows that this right-hand side also always has to be positive. So this restrains the values that beta can take in the trajectory. Namely, the following equation has to be satisfied in order for this right-hand side to always be positive. So do you see how beta equals 0 here corresponds to the perihel? So epsilon is larger than 1, and the perihel is obtained when this term here in the denominator is at its maximum value. The maximum value is obtained when beta is equal to 0. When beta increases, epsilon cosine beta starts to decrease down to a minimum value such that this is still positive, but at some minimum. And then R increases. So when we choose beta 0 equals to pi, we again have the situation that beta is measured from the perihel. Whereas in the elliptical case where we had positive p, we had to choose beta 0 equal to 0. And to see this, we could just have written down this general form in our analysis of the Kepler problem. Instead, we anticipated the events a little bit. We said that before arriving at this result, we chose beta 0 equal to 0, and then said, okay, this will correspond to the angle being measured from the perihel. But we could just as easily have seen it from this equation here. So just keep in mind that the sign of p here requires a different choice of the integrational constant if we want the angle to be measured from the perihel. If we don't want this, then fine, you can choose whatever you want. But it's convenient. So our equation which describes the trajectory is given here, or alternatively here. So let's try to analyze this equation a little bit to see how the trajectory looks like, what it looks like. And one thing that can be good to start off with is to consider the asymptotes, or the limiting cases for this equation. So we have that, for instance, as r goes to infinity, the denominator should vanish. And this happens when the angle is equal to psi, where psi is defined in the following way. So the denominator vanishes when the angle describing the trajectory equals psi, which is some quantity we have introduced, given like this. So let's try to sketch this trajectory now. We have large M here. And we know that the trajectory should be a hyperbola like this. Then psi should be given here. It's the angle characterizing the trajectory as r goes to infinity. And similarly here. So if M is situated here at some time, then beta is the angle characterizing the motion of the position of the particle at any given time. It's the equivalent of what we called theta in the Kepler problem. So psi characterizes the asymptotes of the trajectory, whereas beta characterizes the actual position. The scattering parameter is given here by S. So it's a quantitative measure of how the incident particles are approaching the scattering center. At what sort of distance? Yeah.
Should the beta be measured from large force?
Yes, sorry. You're absolutely right. So we have beta here, and we have the scattering parameter S here. And so what remains to be defined is the scattering angle. So this angle right here is the angle between the incoming and the outgoing trajectory. So it's the scattering angle. So you see that if theta is equal to 0, it corresponds to the particle simply passing the scattering center without deviating at all. Okay, so this is the situation we have at hand. And just like before, the scattering angle plus 2 psi, designating the two asymptotes, is equal to pi. And note that in the way we have defined psi, just as in the initial example we considered for the differential scattering cross-section, psi is measured here relative to the perihel. This is the perihel. Okay, so in order now to calculate the differential scattering cross-section, what do we need to do? If you were to describe, just in words, what quantity do you need to calculate to obtain the differential scattering cross-section? Right. We need to know theta as a function of... Yes, precisely. Because if you recall the definition of the differential scattering cross-section sigma is given as s over sine theta and then multiplied by ds d theta. So we need to know s as a function of theta to find its derivative. So we need to find s as a function of the scattering angle. Or alternatively, the scattering angle as a function of s. We just invert the relation. So then we should have some kind of strategy. We should think about how can we obtain this. Well, we have the eccentricity. We know that it's larger than 1, and the eccentricity depends on the energy. I've erased it. But the eccentricity depends on the energy, and we know that the energy can be related to S by this conservation of angular momentum. So if we're able to obtain some relation between the scattering angle and the eccentricity of the orbit, we would be well on our way. Now, from our analysis of the asymptote, we know that cosine of psi is equal to 1 over epsilon. And at the same time, we know that psi is related to theta in the following way. So if we insert psi from this equation into that, we obtain this. So now we're cooking. We have the scattering angle related to eccentricity, which depends on S. So from this relation and the definition of epsilon, we get this. So the reason I've mucked about with this cotangents is that I wanted something that depends on epsilon squared, because epsilon is defined as the root of 1 plus this coefficient times energy. So instead of having to drag around this root, I now obtained the square of epsilon. And now I can isolate S here. And here we go. The scattering parameter S as a function of the scattering angle. So we now need to compute the derivative of S with respect to theta, and the absolute value of this. Which is obtained like this. So by inserting this expression into our definition of the differential scattering cross-section, we obtain the following. And this is our final result, which is Rutherford's scattering cross-section. And as always, when we obtain the final result, we should take a moment, sit back, and consider this expression, if it makes sense physically. So there are a few things to note here. First of all, we see that the scattering cross-section is proportional to the strength or the magnitude of the charges. Well, this seems reasonable because the stronger the charges are, the stronger the scattering should be. So that seems okay. Also, we have a 1 over energy squared dependence. Does this make sense? Is this reasonable? I see you nodding. How come?
Because of the time argument we used earlier.
So the larger the energy or the faster the particles move, the less time they should spend inside the scattering potential. And hence, the effective area over which the particles are scattered should be smaller. So the scattering cross-section diminishes as the energy increases, which also seems reasonable. Now, this is the differential scattering cross-section. So it makes sense to define the total scattering cross-section like this. It's the integral over the differential scattering cross-section over all orbital angles, d omega. And as argued in the previous lecture, we have this rotational symmetry due to the central forces in play. So we have this 2 pi symmetry around the incoming axis, meaning that we can extract this factor of 2 pi and simply perform the integration over theta. And this total scattering cross-section has a straightforward physical interpretation. It basically means the total effective area over which the particles are scattered. It's the total area in which the particles will experience the potential. Now, in our particular case of the Rutherford scattering cross-section, we know that sigma of theta, the differential scattering cross-section, goes as sine raised to the power of 4 inverse of the scattering angle. And if you insert that into the formula for the total scattering cross-section, you will see that it diverges. So the total scattering cross-section diverges. So please take 1 minute to discuss with your neighbor, what does this mean physically? How can we have an infinite scattering cross-section? All right, so should we discard this result as something unphysical, or does it have a natural explanation? Any ideas?
Because of the range of the electromagnetic interaction is infinite,
Mm.
you will always have a probability of scattering.
Yes, exactly. So what this means is that regardless of from where the particles are incident, regardless of the scattering parameter S, they will always experience some scattering from the Coulomb potential. So regardless of S, the incoming scattering parameter, the trajectory of any particle will be deflected. To conclude this treatment of the scattering cross-section, I would like to make one comment. So we basically assume that the large m was much greater than small m. So the heavy particle wouldn't be affected. It would remain stationary. And in effect, the lab system would be equal to the center of mass system, because the center of mass would remain stationary. And this simplified our treatment, our analytical consideration, because we considered one particle to be stationary, whereas only the other particle was moving. However, Rutherford's formula, which we have derived, is always valid in the center of mass system. So it means that we can relax our assumption of large m being much greater than small m, and thus having, for instance, comparable masses. And as long as we consider the center of mass system, this formula will still be valid. So assume that we're in the center of mass system, and the center of mass is here, which now is stationary. In the lab system that we considered, if the masses were comparable, the center of mass wouldn't necessarily be stationary. In the center of mass system, the situation would look like this. We would have an incoming particle here and an incoming particle here, in such a way that the center of mass would remain fixed. So then the scattering angle would be the angle between the two trajectories. Are you raising your hand? Or? Okay. And this angle would then be what enters Rutherford's scattering formula. So it's important to keep in mind actually the first thing we proved when starting with these two-body considerations, namely that if you have a two-body problem with central forces, meaning that the interaction between the particles only depends on the relative distance, it can always be reduced to a one-particle problem, a one-body problem. So it makes sense that this formula should also be valid in the center of mass system, due to the fact that it's only the relative distance between the particles that matters. All right, we're going to move on to a new topic. The kinematics of rigid bodies. And so let's define some of the terms that enter this title. So by a rigid body, we can rigorously define this as a system of point masses that obey holonomic constraints. So keep in mind, holonomic means that we can write the constraint as a function of the coordinates equals 0. And these constraints should express that between any pair of particles, the distance is fixed. And by kinematics, it's sort of a qualitative word that we use for the nature or character of the motion. So what does the motion look like? Okay, I guess I'll see you next week.